Hello, knowledge seekers. In this episode of 20-Minute Books, we delve into the intricacies of the cosmos with Reality is Not What It Seems by Carlo Rovelli. This enlightening journey bridges the expanse from the philosophical inquiries of ancient Greece to the enigmatic realms of quantum mechanics. Rovelli, a distinguished theoretical physicist at the helm of the Quantum Gravity Research Group in Marseille, France, offers a concise and accessible exploration of the pivotal moments and transformative theories in the history of modern physics, while also daring to ponder the unresolved enigmas that puzzle today's scientific community. Crafted for the inquisitive minds of science enthusiasts, students, and professionals in the field of physics, as well as anyone drawn to the profound mysteries of the universe, this book ensures an intellectual adventure. As you immerse yourself in Reality is Not What It Seems, prepare to unlock the secrets that lie at the very heart of existence, guided by one of the foremost thought leaders in contemporary science. Join us to uncover the fundamental truths that construct our understanding of space, time, and reality itself. Reality is Not What It Seems, The Journey to Quantum Gravity. Introduction. Embark on a voyage through the cosmos of modern physics. Join us as we embark on an intellectual odyssey through the cosmos, an exploration that delves into the history of human thought on the hidden nature of our universe. For centuries, from the musings of ancient philosophers to the groundbreaking theories of modern scientists, humanity has striven to decode the fabric of reality. Let us rewind to the era before the 20th century boom in scientific understanding, where many threads were woven in preparation for the tapestry of contemporary physics. In our journey, Albert Einstein emerges as a pivotal figure, his theory of general relativity reshaping our comprehension of time, space, and gravity. Meanwhile, the jigsaw puzzle of quantum mechanics begins to piece together a picture of the subatomic world, one that is strange and full of paradoxes. Together, these fields sketch the two grand columns that uphold the temple of modern physics, and yet they stand somewhat askew, at odds with one another in fundamental ways. In this narrative, you'll uncover the ancient philosopher whose thoughts on atoms echo through the ages, the intriguing conflict between the twin bastions of physical theory and the curious grains that may constitute the very fabric of the space that envelops you, as suggested by the theory of quantum gravity. Prepare to be transported through the breakthroughs and enigmas that have shaped our current understanding, and continue to puzzle those who search the stars and delve into the quantum realm, seeking answers to the universe's most enduring secrets. Part 1. From Myth to Mathematics. Tracing the genesis of scientific thought. Long before the dawn of modern science, the canvas of human understanding was painted with myths and legends, celestial gods, and capricious spirits that held sway over nature's mysteries. This tableau of mythical explanations started to shift with the dawning of critical thought in ancient Greece around the 5th century BCE, where reason began to take the helm. Picture a thinker like Anaximander, wielding observation and logic, dismissing the divine hand in weather patterns, and instead explaining rain through a process we'd recognize as evaporation, a radical notion that saw clouds not as divine vessels, but as natural reservoirs of sky-bound water. In this crucible of thought, Democritus presented a revolutionary idea. The entire universe was a tapestry woven from unseeably small particles, atoms. These atoms, he surmised, must have a limit in how far they could be divided, a nod to the concept of spatial extension, which implies matter cannot infinitely shrink, yet must take up space. The baton of progress was carried on by luminaries such as Plato and Aristotle, who championed mathematics as the language capable of unveiling the cosmos's secrets. Fast forward a few centuries to meet Ptolemy in the 2nd century CE, whose genius in mathematics illuminated the heavens, giving us formulas to chart the celestial dance of planets. Leapfrogging over the millennia to the Renaissance, a revival of these ancient tools of reason and mathematics took root. Figures like Copernicus challenged the geocentric model, placing the Sun, not Earth, at the system center, a cosmic reordering that reshaped astronomy. In the 16th century, Galileo peered through the lens of the nascent telescope to spy upon a textured moon, Saturn's ethereal rings, and the moons of Jupiter, thus extending our gaze to the vast beyond. He championed a tradition of rigorously tested experiments, laying the groundwork for what we call the scientific method today. Through experiment, Galileo eventually disrupted the notion that objects descend at a steady pace, discovering instead the concept of constant acceleration, that any object dropped on Earth would pick up speed at a rate of 9.8 meters per second every second, a profound insight marking our first mathematical law for terrestrial motion. With that, the seedlings of what would become a grand scientific revolution were steadily, inexorably taking root. Part 2, From Newton's Apple to Einstein's Relativity, a gravitational shift in understanding. Imagine the Enlightenment as a forge, its fires stoked by the minds of great thinkers. Here, in the 17th century, Isaac Newton was welding a new framework for understanding the heavens and the earth. Inspired by Galileo's experiments, Newton envisioned a world where the forces causing apples to fall and moons to orbit were one and the same. His theory of universal gravitation painted a universe where every mass exerts an attractive force upon every other mass, a revelation that bound the earthly and celestial realms more tightly than ever before. Newton's deep insights notwithstanding, he had a profound sense of the mysteries that remained, the unseen forces yet to be uncovered, a sentiment that echoed through the halls of time. Advancing into the 19th century, Michael Faraday and Clerk Maxwell spotlighted a new force: electromagnetism. Suddenly, an understanding emerged that molecules and electrons were coupled by electromagnetic forces, and critically, that these forces didn't act across a void, but through a pervasive, imperceptible matrix known as the field. Conceptually transformative, the notion of the field suggested a more interconnected and dynamic universe than ever imagined. However, the scientific canvas was awaiting another dramatic upheaval. Enter Albert Einstein in 1905. Einstein's theory of special relativity was poised to challenge and extend the Newtonian worldview, uniting it with emergent knowledge. Special relativity proposed that the planes of time and space themselves were malleable and dependent on the motion of an observer, a counterintuitive vision where time no longer ticked uniformly across the universe. With the unveiling of special relativity, Einstein heralded a new epoch in scientific thought, a world less certain and more wondrous than ever before, where even the steady tick of time was not immune to nature's dance. And yet, this was merely the precursor to even grander revelations that would further unravel the threads of our understanding. Part 3, The Cosmic Symphony of General Relativity and the Echoes of the Big Bang. Albert Einstein, already distinguished by his work on special relativity, ascended to new intellectual heights in 1915 with his exquisite theory of general relativity. It was a conception so profound it intertwined the very fabric of space with the matter within it, to a ballet of cosmic forces that was remarkable in both scope and elegance. Imagine space not as a desolate void, but as an entity, a dynamic gravitational field that interacts with and is shaped by the matter it cradles. Within this Einsteinian vista, mass commanded the stage, introducing curves and contours into the expanse of space itself. These distortions guide the cosmic choreography of matter, crafting the orbital pathways of bodies as surely as marbles roll along the curved surfaces they encounter. Gone were the bygone days when space and matter were treated as separate players. Einstein's vision fused them into an entangled duet. This newfound understanding of gravity represented a revolution, pulling Newton's apple from its 17th century tree and into the modern era. Einstein's wizardry with equations reached further. whispering secrets about the universe's very genesis. Facing the great divide between a universe that was either finite or infinite, Einstein proposed a synthesis, a cosmos that is finite in volume yet boundless, akin to journeying around the Earth's surface without ever encountering an edge, finite yet without boundaries. This led to a startling contemplation about the architecture of the universe, with the possibility that, by marching in one astronomical direction, one might eventually loop back to the starting point. Yet, this bounded universe disagreed with the observable fact that the heavens hadn't collapsed in on themselves. To rationalize this, Einstein deduced that the cosmos must be in a state of expansion, rebuffing the inexorable grip of gravity. It was this line of reasoning that paved the way to the monumental concept, the universe potentially emerging from a cataclysmic event, a Big Bang, where the outward rush of matter overcame gravitational clutches. Thus, general relativity gifted us a picture of the cosmos, both mesmerizing and revelatory, with the Big Bang echoing as the universe's birth cry. Part 4. Quantum Mechanics. Peering into the atom's heart reveals nature's unexpected triad. As the universe's grand scales bowed to the elegance of general relativity, an equally profound revolution was unfolding in the minuscule realms of the subatomic, the advent of quantum mechanics. This revolutionary theory peeled back the layers of atomic and particle phenomena, granting us an unprecedented glimpse into the staggering intricacies of the micro-world. Within this quantum domain, three cardinal truths arose like pillars from the mist: the nature of reality as granular, relational, and indeterminate. The journey into quantum mechanics began with Max Planck's bold leap in 1900, as he wielded the concept of quanta, discrete packets of energy, as a mathematical convenience to simplify his calculations. Planck was as astonished as anyone to find his theoretical construct aligning with reality. This idea of granularity gained further validation when Einstein, in a stroke of insight, envisioned light itself as a stream of particles, a photon shower. Soon after, Niels Bohr, the Danish luminary, ventured deeper, finding that electrons possessed fixed energy levels, akin to distinct steps on a ladder. It was a departure from the assumption that their energy could span a continuous spectrum. Werner Heisenberg, with his pioneering work in the 1920s, unveiled the second quantum pillar, relationality. His revelation that electrons don't possess definite locations until they interact with something else overturned centuries of deterministic assumptions, proposing that existence itself hinges on relationships. This quantum stage led to the third and most perplexing aspect: indeterminacy, embodied in the principle bearing Heisenberg's name. This principle suggested that physical events, such as an electron's position, can't be predicted with certainty, but only with probabilities. It was an eviction notice to the certainty that had long been a tenet of physical science, welcoming a new era where possibility and probability reign supreme in the subatomic realm. Thus, quantum mechanics has stirred the pot of understanding, suggesting a universe where even the building blocks of matter are subject to a form of cosmic chance, where reality itself is a dance of probabilities, connections, and granularities that challenge our deepest intuitions. Part 5. Quantum Gravity, Weaving the Threads of Space-Time's Quantum Tapestry. In the present era, physicists stand at a crossroads, confronted by a puzzling contradiction that splits the fabric of understanding down the middle. The magnificent structures of general relativity and quantum mechanics, each robust in its domain, seem unable to coexist peacefully in the grand unifying tapestry that scientists yearn to create. The theory of general relativity glories in a smooth, contoured landscape of continuous space. Meanwhile, quantum mechanics insists on a digital universe, painted in discrete strokes of energy and matter. Bridging this chasm is the ambitious goal of quantum gravity, a quest to harmonize the celestial curvature of Einstein's vision with the dotted imprints of the quantum world. The first groundbreaking assertion of quantum gravity is that space, much like matter, is granulated, its fabric stitched together from indivisible threads that defy further subdivision. It is an echo of the thoughts of Democritus and of Bronstein, whose 1930s research posited that space was made of these indivisible pieces, grains we now measure in units called Planck lengths, an unfathomably small span that marks the boundary of space's divisibility. Terminology like atoms of space or quanta of space reflects this newfound awareness that the void isn't void at all. It is a landscape dotted with the smallest conceivable plots of spatial real estate. The second profound declaration of quantum gravity pertains to the enigma of time, itself a concept turned on its head by special relativity over 100 years ago. What was once thought of as an absolute constant, as dependable as the ticking of a clock, is revealed to be a variable entity, with its rhythm disrupted by the geographical contours of the universe. Astoundingly, where you are determines how time flows. Height correlates with speed. A clock perched on a table ticks fractionally quicker than its twin relegated to the floor. The result is a profound reimagining of physics where time, stripped of its constancy, is exiled from the fundamental equations that seek to describe the universe's raw behavior. So profound is this paradigm shift that in the realm of physics, it's no longer accurate to say that things happen within time. Some physicists go further and suggest that time, as we traditionally conceive it, doesn't exist. It's a persistent illusion, not inscribed into the bedrock of physical laws. In the embrace of quantum gravity, the very notions of space and time are being rethreaded, forming the vanguard of our understanding in the relentless march towards a theory of everything. Final summary. In the grand tapestry of physics, human curiosity has charted a course from the myth-laden interpretations of our ancestors to the mathematically precise understandings of today. Born from the rational seeds planted in ancient Greece, science has evolved through the methodical rigor established in the Middle Ages and the insightful principles laid down by Newton, wherein time and space were once absolute. Yet, the 20th century signaled a paradigm shift with Einstein's theory of general relativity, which reshaped our conception of the cosmos as a continuum where mass and space interweave. Alongside this revelation came quantum mechanics, with its atomic intricacies and probabilistic nature, challenging the certainty that classical physics once promised. Now physics stands before its perhaps greatest challenge: the reconciliation of the celestial ballet of general relativity with the quantum realm's granular choreography. As physicists strive toward this unifying theory, we find ourselves in a world that seems more magical than mundane, where time's relentless march may be mere illusion and the fabric of space is stitched with indivisible points. We are left in awe as the frontier of knowledge expands, reminding us that in the universe's grand narrative, reality is not what it seems, but an ever-evolving enigma that beckons to be unraveled. Thank you for joining me today on this journey of learning and discovery as we explored the insights of another thought-provoking book in our growing library of knowledge. If you've enjoyed our time together, please take a moment to follow our podcast, give us a 5-star rating, and share 20-minute books with other knowledge seekers. Your support truly means a lot. Don't forget to join me again in the next episode, where we will delve into another enriching book. Until then, happy reading and happy listening.